this is a very sort of diverse audience. So I was trying to think about what level I should pace this course. I have in the end decided to focus a lot on like the terminology, like a lot of the basic definitions and so on, with some few examples here and there, and I also have a lot of like simple exercises which hopefully you should all be able to follow. I mean, if any of you have already come across some of this stuff, I mean, hopefully you can think of this as like a gentle revision of the stuff that you've learned before. For some of you, you may be seeing this for the first time, and hopefully, this by the end of this, you'll all be able to follow this topic. So I wanted to just begin by showing you, showing you this. So this is a map of the London Underground from 1908, and I'm sure you've probably all seen maps like this before. But what I want you to tell me is, when you see a map like this, what's the sort of information? Let's assume that you're a traveler over here. What's the sort of information that you can sort of extract by just looking at this map?
What is the next stop? If I'm at some stop, how many stops do I need to cross to get to a certain point?
Well, for sure, that is a bit of information. What other information can you get from this map?
The different junctions where we are meeting different stations.
Okay. Okay.
The extent of spread, maybe.
Like, sorry?
The extent of spread, area covered by the different paths.
The area covered by, okay, you mean the total distance over here?
Yeah.
Yeah.
How to change line?
Yeah, how I define like between two points.
Uh,
Changing
no, it doesn't tell you how to minimize time. It gives you the junctions where you can change to. Yeah, it gives you that. Okay. The shortest part is something which potentially you could infer from it, right? But that's not something which automatically you will get from that. But yeah, you can infer from that. What the other sort of
junctions.
Sorry?
Related directions.
Oh, related directions, yes, for sure, definitely, yes, because you see, you have all the sort of how the path curves and so on. Yes, definitely. Anything else?
Where is it possible to go?
Where it's possible to go? Yes, definitely, yes.
Clusters and important.
Yes, definitely. That's another thing. Yes. Because there could be some areas where you have a lot of stations. Like for example, you have a lot of stations over here, whereas here you just have one station, then after some time another station, and so on. So here you have a huge gap between these stations, and so on. Yes, that's definitely true. Anything else?
Important areas.
Yeah, true. Yeah. Yes, points where you can. So over here, these two lines sort of meet up over here. You can go from the red line to the green line, and so on. Yeah. But okay, fine. So there's a lot of information that, as the more you look at it, the more information you can extract from this. But can you let's say that you are a passenger. So let's just say you're getting on the train over here, okay, at Highbury, right? How much of all this information that you just mentioned is actually relevant? Like, what is like the most relevant things amongst all the things that you mentioned so far? What are the most relevant things that you need to know? The destination, of course. So basically, you need to know what line you're. Suppose I'm going here. I need to know this is on the blue line and I am on this line. Yes, that's one thing. Then,
How many stations I need to go through to get some?
yes, you need to know that.
Based on the number of intersections, like you can find, like there might be a varying number of stations that you might need to cross.
So you need to know where the
Various
intersections
paths
are.
that
You need to know where the intersections are, because suppose I'm on this line, and you know, okay, how do I go onto the blue line? So if I'm, so you need to know that. Yeah. That's pretty much it. I mean, so once you know this, then everything else that you'd all discuss, these things you can either infer from that, or maybe it's not relevant. Like for example, if I'm going from Highbury to Old Street, I don't need to know how much distance there is between the two. I know if I'm on the train, I'm going to go one stop and then another stop. I don't need to know how long. And another thing is like there's a lot of like curvature and so on based on the exact location of each stop. I don't necessarily need to know that, right? All I know is I'm here, I need to go here. I go 1 stop, 2 stop, 3 stop, So I just need to know that. And so this is the sort of thing that that back in the 1930s, someone called Harry Beck, he was thinking about this. He said, we don't actually need all those details in that map. We can actually just reduce all of the information into something like this, right? Which basically sort of satisfies a lot of the things that we just now discussed. You see, we know, okay, I'm on this line, so these are all the stops on the line. I go 1 stop, 2 stop, 3 stop, 4 stop, and that's something that I can do. And then I know here, okay, here I can change the line. I go from this blue line to this other line over here, and so on, right? It doesn't tell me how far away the different stops are. It doesn't, like you can see here, it's just one, it looks like one single straight line. Well, it's not, in reality, it's not a straight line, but it says, okay, this is just one single path going all the way down these things. There is a little bit of like curvature when you have a lot of paths that are kind of close together. When you have like this line and this line and this line, it's sort of more kind of slightly, you see a little bit of curvature, which tells you broadly, am I going north, south, east, west? But even that, it's not extremely specific, right? But something like this, for a passenger, it's perfect. Basically, you don't need to know more than that. You need to know, I'm here, I need to go here, what do I need to do, right? Maps like this have now become so common. I'm sure if any of you have been on a metro in any major city, you would have seen maps like this. Maybe not so detailed, but you have probably seen maps like this on the metro, right? But so the reason I'm bringing this up right now is that so as we just discussed, this map over here is really just an abstraction, right, of this map over here. And if you think about it, this is also a kind of an abstraction of reality. This is just like an artist's representation of what will be, the expected paths along, going from place to place and so on. Right? So in some sense, it's an abstraction of an abstraction. But nevertheless, yes.
So the thing is that suppose I'm taking the train from. I'm sorry. What was it? No, I mean the previous map.
Yeah. Yeah.
Yeah. So suppose I'm taking the train from Highbury.
Yeah.
And I want to get on the blue line.
Yes.
Let's say I'm going at the end of the blue line on the left hand.
Here. This side.
So I have two possibilities. I can go to the yellow line.
Yeah.
Okay. Then change to the blue line.
So basically, go up like this and come down like that. Yeah. Yeah.
Or I can
go down here.
This end of the blue line and take the blue line from there.
Yes.
Now this map gives me some information that I might take shorter time to get on the blue line if I go directly to the blue line end rather than if I go to the yellow line and then take the blue line. Right?
Well, no, it's not necessarily true though, because you see that if you in this particular example, you see that there are a lot more stops over here. So I mean, so here, it's like it so happens that you spend some time here, spend some time here, spend some time here, for passengers to board the train. Whereas on the other hand, suppose you had only like 2 stops over here, 1 stop, 2 stop, 3 stop, and then your final stop, you would go much faster along this line. So these are things which it's hard to encode that information in the map, right? So for that reason, maps like this are useful, because typically what really matters is the number of stops, right? Really, because in terms of because the trains can speed up or slow down, going from stop to stop. So as you can of course have occasions where maybe there's a huge gap between these 2 stations, but that typically happens only on the outskirts of cities, right? Typically, when you're within the city limits, going from stop to stop is more or less the same time, right? But anyway, I guess the reason I'm mentioning this is because, I mean, even though this is in some sense a very sort of abstract kind of representation of reality, in some sense it does tell you something about reality as well, right? I mean, so there is information which you can extract from this, which has some useful information that you can you can use for your for your purposes, right? And the point is, this sort of network that you look at is in a sense, oh sorry, yeah, so this network is basically something that oh, I don't know what's happening here. Hello? Yeah. Yeah, I don't know what's happening. Yeah, so this network is basically the information that you can extract from this, it depends on how exactly on what are the criteria that was used to sort of construct this. So here the only criteria that was required was I need to know which track it's on, or which sort of route it's on, like the blue one, the red, and so on. I also need to know what are the stops that are before and after, and I need to know where do I change lines. So given this information, I can construct a network like this, and then I can, having this network in my hand so removing all the other information, I can still extract useful information from this, right? And I think this is something that's sort of important to keep in mind when you're looking at networks in reality, right? Because ultimately it's just a sort of an abstraction of something which likely corresponds to some real world sort of set of connections. Depends on how you define the connections, depends on how you define the the nodes, the paths, and so on. But once you're aware of that, then you can really sort of use this for for getting something that may be helpful. So jumping ahead, so now that we've sort of understood how this works, so here is an example of a sort of a kind of a map which you might see today. So these are like the airline routes between all like the major airports of the world, and they're kind of colored according to the longitude, and the various paths they correspond to the connection. Basically, there's a flight from here to here, and so on. So this you could say is okay. So this is very detailed. It's got all this information. I know I'm going from here to here and so on. But then you could ask, okay, fine. Suppose I don't care about the specific location, right? But I can still retain the information about the longitude, right? So I allow this map to sort of be kind of deformed in such a way that the nodes can kind of cluster according to the connections that they have. So what they've done over here is that they've used a layout algorithm where they've essentially it's like you're putting like springs between disparate sort of parts of the network, and you also have repulsion between nodes of the network. And so basically you're just allowing this to kind of evolve, and so it's no longer stuck to any sort of physical location. It's just moving around, and as they've done this, so what you can see is that these kind of clusters are emerging. So here you can see this cluster in North America, and there's a cluster down here, and so and something over here you can see between India and the Middle East is actually they're kind of clustered together more or less, which is not something which would have been so immediately apparent from this map, and so on. And so whereas Russia is sort of like a little bit more sort of isolated, and so on. So but of course, I mean, we can look more into this and try to see if there's anything useful that you can extract from it. But this is just another example of constructing a network where you've sort of just limiting yourself to the information that you're interested in, and just see what you can extract from them, right? Just a few more quick examples before we get to the theory. I don't know if any of you remember the blogosphere. This was a big thing back in my day. This was a very sort of striking example from like one of the early days of the blogosphere, where so basically blogs are like people can post their thoughts and opinions, and then they can have links to other blogs from across the spectrum. And so here they're specifically focusing on political blogs. And the blue one and the red sort of so this is in the context of the US. So just prior to the 2004 US election, they were looking at people who were linking to other blogs, and what their general affiliation of the blogs were, whether they were like Democrat or Republican. And it's not a surprise that people tend to sort of link to other people of a similar sort of opinion or political persuasion and so on. But once they extracted this information and they just visualized this, it became so strikingly apparent that this is the case. I mean, it's almost like it made it very abundantly clear. It's no longer just a feeling we had. It is actually a fact that that people tend to talk to each other of their own political persuasion. So the link basically means that if you're writing a blog post and then you just and you're mentioning something, and then you just give a link to somebody else mentioned this, and it's just like I'll say somebody mentions something about this particular election, and you just give a link to that.
Then shouldn't you link your opponents more, like look there?
I actually yeah, I'll have to see, but I have a feeling that here they were mainly focusing on no, I think it was mainly like reblogging. I think it was mainly reblogging. Yes, sorry. I think that's mainly what it was, because the reblogging basically you sort of highlight you say that this person has written an interesting post and you highlight it. So I think I think it was mainly that.
Blue and red are Democratic and Republicans.
Yeah. Oh no, so I think so the blue links are going from blue to blue, red is from red to red. Yellow is from blue to red, and purple is from red to blue. Yeah, so you see here from a blue to red, that's yellow. So it's like this. So there are some of those links in the middle. So here you see the purple and the yellow links. Okay, and then one last example. This is for sort of a similarity network of musicians which somebody had extracted from this last.fm's data. And so they had their own algorithm to sort of assess how similar different music artists are. And there are like thousands of artists over here. And I think the size of the circle represents how popular they are, how many listens they get. The color corresponds to what style of music, what genre of music. You can see that there is a sort of a kind of a clustering based on genre, although it's not entirely contiguous. You see the green is sort of split into various compartments and so on. So the question is, what information can you get from this? Well, I mean, it depends on the question that you're asking, but certainly streaming companies and the like would find this sort of information very, very useful, because then they can recommend more artists based on the type of on what information they get from this. So yeah, so anyway, so these are just a few examples, and there are like countless more examples that one can find. Yes. I think it's coming from the source. I think so. If the source is red, the link connection is red, and so I think that's what it is. Yeah.
What is the size of the points?
The size, I think, it corresponds to the number of times that they listen to. Right.
So the connection.
The connection is like the similarity. I think if I remember correctly, this is a similarity based on some algorithm which they had. Yeah, so they're using some algorithm based on some relation to this, but also to this, and so if there's enough of of a similarity, then they give a connection. I don't know the algorithm, but yeah.
The size of the node be the number of tracks within that genre instead.
You can do that, but then you kind of collapse the whole network down to just around 10 or 12 links. You can do that also. But then, of course, if you do that, then the question is what information will you be getting from that? Because because then you have a very, very small network, right? So, yeah.
So nodes here are not depend. I mean, the location of nodes are not on
The
actual
location of the
location.
nodes data, they don't depend on anything. This is just on this website. This person has just taken the data and then used some sort of layout algorithm to sort of to organize the sites. And you can see that yeah, so it just so happens that these are clustered together, but they the reason that they are clustered together is just because of a very, very high number of links between them. That's it. So it's the specific location is in some sense you could say is random, but it's not entirely random because it also depends on the the connections. So yeah. Okay.
But then
Yeah.
if a company wants to recommend on the basis of this, then they don't. This map is
They
not
don't
including
need,
the
they don't need this map. No, of course you're right. They don't need this particular map. They need the data we used to make the map.
Okay.
Yeah.
So you can have that kind of map also, which depends on the location, and that might
No,
convey
the
more
location
information
doesn't
than this.
mean too much here. See, the location is just for us to visualize it. That's all. It's so by just looking at it, you can't say all that much. You actually have to go into the data and do some analysis on that. So so this is just to make it look very aesthetically pleasing and so on, to say that look, you can roughly see that this which one is it, metal also is very sort of clustered together. So there's not a lot of overlap between others, whereas I think pop you can see is sort of split all over the place. So it's more for that. This is just more like a kind of a fun exercise. This is but the data used to make this is what is useful for the companies. So okay, so if there are no more questions, then I'll move on. So okay, so now that we have like a very rough idea about this, I want to just go back in time, at least go back to when I was in school. There was kind of an activity which it used to befuddle me. I mean, perhaps I was a very, very naive and dull student, but it used to sort of befuddle me, which was that suppose you're given this object, and you have to draw this without taking your pen off the paper and without crossing any path twice, right? So the question is, can you do this? So would you all like to try this? And if people are able to do it, just raise your hands. You can cross nodes twice, but you can't cross a path twice. Yeah, you can do it. Okay.
Yeah, but
Sorry? Yeah, so you can do this, right? Okay, good. So now try this.
The trick was to fold the page and then something like that.
You have to resort to some tricks, right? But so does everyone agree that this one is much harder, or not harder? Impossible.
You can't.
It's not possible, right? So there is actually a reason for this, and to understand the reason for this, we'll have to go back a few hundred years, and to this particular sort of question. Some of you may have heard of this, which is the 7 bridges of Königsberg. So this is a map of the city of Königsberg back in the 1700s, and so here you see like a kind of a river passing through the city, and there are a lot of bridges, right? So somebody asked the question. The bridges are just highlighted by these circles over here. So somebody asked the question. Suppose I want to kind of visit all the different banks, basically this bank, this bank, this bank, and this one over here. So these 4 banks, and I want to do so by crossing all the bridges, right? But I only want to, I'm only able to cross every bridge once. Right? So the question is, if those are my constraints, what is the route that I need to take in order to achieve this. So does everyone get the question? So okay, so can anyone tell me what they think would be a good route? If anyone thinks they have an idea, they can even come up and do it on the board. If anyone would like to volunteer.
How many places do you need to cover?
So basically, you need to go from this area, right? Then if you do this area, so these three areas, and then this area over here as well, right? And basically, you need to cross all these bridges. Okay, so you need to cross all these bridges, but you can only cross a given bridge once. So how do you do that? You can even simplify the question like this. You can even simplify the question as I just want to cross every bridge, but cross every bridge once. Because if you do that, you'll automatically reach all the banks. So just say I want to cross every bridge, but cross every bridge only once. No, you can start anywhere you want.
There is one bridge that you can't cross twice.
You can come to the same path twice. So suppose I'm here, I can go down and I can come back up here. I can do that, but I can't come back on the same bridge.
If you go straight like this,
So go down like this, okay?
and then you
Go back up, okay? Yeah, okay.
then you go back completely up.
Yeah.
And you cross that bridge again.
Down. Okay, fine. So you cover these four. Then
Then you come back 4.
it's not possible. Okay, so you're thinking not possible. Does anyone still think it might be possible, or?
It has to be possible. If it's possible, it won't be there.
Sorry, where? Yeah. Down. Okay. Top. Okay. Come back down. Bottom. Correct. Down. Okay. Okay. So it looks like people are struggling. So does anyone want to have one last attempt? No. Okay. So unfortunately, the answer is that it's impossible. And so this was actually shown by Euler in 1736, right? So he basically he simplified this whole thing to just looking at different banks, right? So say they have bank A, B, C, and D, and each bridge he just putting a link over there, right? So I have a link from A to B, another one, and then 2 links from B to C, and then these are the links as well, right? So suppose I do this, then essentially I can view this whole problem in terms of sort of a network like this, right? So I have these banks A, B, C, and D. I have 2 connections from A to B, 2 connections from B to C, and then a connection from A to D, B to D, and C to D, right? So that's exactly the same thing over here. So now if I have this, the question is, how do I have a path around this network such that I don't cross any link twice? And it turns out that only if you are starting at a node or ending at a node, then you can have an odd number of links. So for example, suppose I'm starting from, okay, let's just imagine that, okay, how do we do this? So this has 3, this has 3, this has 4, this has, yeah. So let's, if we remove the link from B to D, okay, so then I say, okay, if I'm going to go down up like this, and then go here, and then go down, come back like this. So then now the B to D link is not there, and then I'm fine, right? So I have, so my one terminal link has got 3 links, another terminal link has got 3 links, right? So starting from A, going to C, but unfortunately B has also got a link from here, B to D. So there are 3. So actually there are here all 4 nodes have an odd number of links. So it is not possible to do, right? And this particular sort of proof that Euler came up with essentially formed the basis of what later was known as graph theory. Graph theory is essentially just what we use when we look at networks, right? Because a network is basically, very broadly speaking, just a connection of a network of, so it's is a bunch of connections between entities, and this can be analyzed as a graph, right? And a graph is just that, something like this. Right? So you basically have objects and connections between them. So a network is just a graph where the objects and the relations have certain attributes. That's about it. Or I mean, so we're saying that okay, this particular bank has some attributes. This bank has some attributes, and the link has maybe there is this has some weight associated with it, and so on. So we can ascribe various attributes to this, but at the end of the day, it's just a graph, and we'll talk in the subsequent slides about all these attributes and so on. But that's basically it. Okay, so maybe for a while I will start now discussing some of the fundamentals of network theory, getting into some of the basic definitions that you need to know. We will break at some point for lunch, but let's see how we go. Okay, so a network or a graph essentially has to have these two components, as I just mentioned, right? So it needs to have objects. The objects could be anything. It depends on what you're describing. And it needs to have, so the objects are what are referred to as nodes or vertices, and they need to have connections between the objects, right? And the connections are referred to as links or edges. Given a network, one can start talking about certain properties of the nodes, right? So what are the properties that a node could have? So essentially, without mentioning anything else, all we can say about a node is that okay, so each node has a certain number of connections, right? So node 1 has 1 connection, 2 has 3 connections, 4 has 3, and so on, right? So this information is what is typically referred to as the degree of the node, right? Just the total number of connections that it has, right? And so here are just some examples, right? For just some very simple networks. So over here you see this blue node has a degree 1. In this network, this blue node has a degree of 2. Here this node has a degree of 3, and so on, right? So this is like the most sort of basic information that you can possibly have, just how many connections that a given node or an object in a network has. Okay. Yeah. Did I skip? No. Yeah. So you can also have other bits of information in the network, right? So for example, the connection between a pair of nodes, it could have a direction associated with it, right? So for example, it could mean that I mean, it depends on the interpretation, of course, right? So but in an abstract sense, a link can have a direction, right? So you could go from 1 to 2, but perhaps not vice versa, right? And similarly 2 to 4, and so on, right? So as I said, what the direction means will depend on what the network is describing, right? So for example, it could mean that, you know, like if we're talking about some social network of people, and we're talking about the interactions could be like who gave who a present, right? So it could be that person 1 gave person 2 a present, and so on, right? You could also have links going the other way. In this network, I have not shown it, but you can have that as well, right? So, but that's what a directed network means. A directed network just means that every edge or link in the network has a direction, right? And now in a network like this, obviously, you can look at the link in a number of ways, right? So now because the link has a direction, you can talk about the number of links that are coming out from a node, and that's what's called the out degree, right? So from node number 2, there are 2 connections going out, but 1 connection coming in. So that's called the in degree, right? So node number 2 has an in degree of 1 and an out degree of 2, and the total degree in plus out is just 3. Right? And in the same manner, you can compute the in and out and total degree for every node, right? And the in degree and out degree can of course be different, right? So so the in degree and out degree only make sense when you have associated direction for each link. Okay, and then another type of attribute that you can give to a link is you can give it some weight, right? So the weight could correspond to maybe let's just talk about a scenario where, for example, you have a bunch of individuals, and you're looking at the number of times that an individual interacts with a neighbor. So maybe 1 and 2 they interact once, 2 and 4 they interact 2 times, 2 and 3 2 and 5 they interact 3 times, and so on. And so maybe we say, oh, we need to know that information. So I don't just want to know that 2 interacts with 4. I need to know how many times they interacted with 4, right? And so on. So that information you can provide by giving the link a weight, right? And so that's the sort of thing that you have over here. Oh, sorry. Actually, I've done it a bit differently over here. I'm sorry. So I think here what I've done is I've labeled the link. So this is link number 1. I've given a weight of 1. Link number 2, I've given a weight of 2. 3 I've given, and so on. But you get the picture. So but the point is you can ascribe a weight given with that. And so over here I've given a weight of 0.5. Maybe it doesn't make sense that I interact half a time, but in a different context, half you could have an interaction. Half could have some meaning. You can give any weight as to and unknown. Okay. All right. Okay. And some other types of networks. So so these are some things which you probably will come across when you look through the literature. So you could have networks that describe a relationship between 2 different classes of objects, right? So for example, like you have this scenario over here. You have one class of nodes 1, 3, 4, 5, another A to E, and you have connections going from class 1 to class 2, right? So this could, I mean, a very simple example could be like you will soon experience this when you're doing the group projects, right? So you could all be the students, and so you could be the groups, right? So basically this is group 1 has 3 people, group 2 and so on, and these are the mentors, right? So basically you could say, okay, fine, group A and group B are going to go to mentor 3, group D is going to go to mentor 2, and so on, right? So it could be something like that. And another type of network is called a multiplex network, wherein essentially you see that these exactly the same nodes occurring again and again, right? So 1 to 5, 1 to 5, 1 to 5, and so on, and you have links between them, right? But there are different types of links. So here you have some blue links, some red links, and green links. So what could this mean? So it means that you have the same set of nodes, but different types of links between them. So for example, like you could say that these are different cities, right? So so you have 5 cities over here, and these are the different sort of the ways that you can connect by bus. These are the ways you can connect by train. This is the ways you can connect by flight, and so on. It could be something like that. But in each case, one is the same. So it's city 1, city 2, city 3, and so on. But these are different ways you can connect between them. So this is what's called a multiplex network. I won't get too much into detail about bipartite and multiplex networks for the rest of the course, but I just thought I need to mention this because this is something which you probably would come across quite often. It just means that it's the same node. So 3 is the same. So it's just for ease of illustration, I put them in 3 separate layers, but strictly it's just one layer. But the links are different. So what I could have done is I could have shown a single layer and just put 3 different types of colored links between them. But
putting one in the middle and then
yeah. So I could have just had one layer, but just had all the color links together. Just it look a bit messy. So I just shown it as 3 different layers. I mean, this is how typically sort of understood as well, because essentially the properties of this layer, they may be independent of the properties in the other layer. So one can independently study this and that and so on. But you can also have actual connections between them. But as I said, so that's sort of a separate story. But in the simplest case, you can just have this. You can just say that you have the same links, but different types of connections between them.
and the layer doesn't need to have bipartite.
No, here it's not bipartite. In fact, it's not bipartite because the nodes are the same. Yeah, the nodes are the same. Yeah.
Would the initial example we did with the stations and different lines being something like that? The blue line, the green line.
Yes, actually, you could do that. Yeah, that could be an example.
But the stations will be the same.
Okay. Okay, I can still talk for a bit more. So okay, so let's now, okay, so now that we've talked about some very basic stuff, let's move on to the adjacency matrix, right? So let's just say, okay, I have a network like this. Okay, this is a very simple network, right? So in some sense, you can analyze the properties of this network by just looking at it, because it's so small, and so there are very few number of links. But in general, networks typically can be kind of large, and they could have huge number of links and so on. So just looking at it and trying to extract properties is really it's very bad idea. Right? So we need to have a more efficient way of doing this. So for this reason, people typically describe a network in what's known as the form of what's known as an adjacency matrix, right? So in an adjacency matrix, essentially, so you have like rows and columns corresponding to the different nodes. So here you have 5 nodes, you have 5 rows and 5 columns, and the entries of the matrix will be either 0 or 1 if you have a link or if you don't have a link, right? Of course, this is for the case of an undirected network, so that the links have no direction. So basically, if you have a link from 1 to 2, you have a link from 2 to 1, and so on. So you see that for this particular network, this matrix is symmetric, right? So hopefully this part you get, right? So this is it's very simple stuff. But on the other hand, if you have a directed network, it need not be symmetric. In fact, it's most likely not symmetric. You just have you have over here along the rows you have the sources, and along the columns you have the target, and you just fill up the entries of the matrix depending on whether or not a link exists. So you have a link from 1 to 2, you have a link from 2 to 4 and 2 to 5, and so on, right? Although I have to mention that this particular convention of having the source along the rows and the target along the columns is not necessarily a universal convention. In fact, since people analyze networks in so many different fields, depending on which field the particular researcher is from, they might have a different convention. So some of them may choose to put the source along the rows, and others may choose to put it along the columns, which is why it's very important to to look carefully and through the descriptions when you're reading papers on this to see like how exactly they've defined it, right? And also it's a good practice to do it yourself. When you are presenting an adjacency matrix, you should be very clear about what the rows and what the columns represent, which is the source and which is the target, right? When the case where you have directed networks. Okay, so now that you have an adjacency matrix, you can do a lot with it. So, but the most simple thing that you can do is you can just find the degree, right? So here I'll have to I can count. I can say, oh, this 2 has 1, 2, 3 links and so on. But if you give me a network with some thousands of nodes, I can't count all of them, right? But on the other hand, if you give me the adjacency matrix, I can just take the sum along either the rows or the columns, I mean for the case of an undirected network, and then I just say, okay, so here I think the sum is 1, 3, 2, 3, 3, and so on. And I know it immediately. I don't need to go and count it, right? And I could even do along the columns for this case. But for this network, I can find the in degree or the out degree by going along the rows or columns depending on what I'm interested in, right? So if this is the number of links leaving this node, these are the number of links entering this node, and so on. So you can very quickly do these sorts of calculations once you have this information. Hopefully that's very clear, right? Okay, yeah, maybe I'll do for another 5 minutes and then we'll stop. So okay, so so now that you have the adjacency matrix, what are the other things that bits of information that you can get from this? So let's look at this network over here, right? So you can see here that you have a lot of links between the various nodes, right? And this is how the network would look like in terms of an adjacency matrix, right? So you can see by looking at this that a large number of the links, the entries are 1, right? Which means most of the nodes have a connection between them. On the other hand, in this network over here, you see that it's mostly filled with zeros. Right? You just have a few ones, and so these are typically referred to in a very loose sense, because there's no strict definition for this, but loosely a network is said to be dense if most of the possible links are present, and is said to be sparse if most of the links are absent, right? So when you have when you're presented with an adjacency matrix, which could have, like, say, hundreds of nodes or whatever, by looking at the density, which is basically the probability that there exists a link between nodes I and j, or essentially it's just basically the fraction of links that exist, right? So basically, if a density is 1, it means that the network is fully connected. All nodes connect to all other nodes, right? If the density is 0, that means there is no connection between any of the nodes, right? So, but if density is intermediate, somewhere between 0 and 1, it means you have some fraction of connections between the nodes, right? So typically, when rho is close to 1, it's said to be dense, but it doesn't have to be very close to 1, but even fairly high. When it's close to 0, it's said to be sparse, right? So these are some terms that people tend to use when talking about these sorts of networks.
What would be the probability in that? 1 by 8.
Well, the thing is, for here, you can actually calculate this exactly, right? So basically, you know, huh?
To take the possibility of any existing between two nodes.
Yeah.
1 by 8.
So 1 by no. Right. So basically, from this you can compute that. Yeah.
If rho is 0.5, would you classify it as dense or
Probably not. Probably it would be neither dense nor sparse. I think typically dense and sparse are typically they used to talk about the extreme cases when it's very where most of the links are present or most of the links are absent. But like I said, there's no like very precise definition about this. It's just more a colloquial term which people use to talk about networks where most links are present or most links are absent.
Also would depend on the domain I'm thinking, the density and sparsity, the domain.
Perhaps, yeah. So yeah, but just to let you know about the terminology. Okay. So one thing that how many slides do I have? 1, 2. Okay, I'll do one thing. I'll do the next few slides because there's a question at the end, so I wanted to do that as well just before we stop. So so now that so suppose you have a network that which is presented to you, you can actually talk about the routes that you could take along the network, right? So we had the example of the train station a while back, right? Suppose I say I start here, I go from here to here to here, and so on. So I just follow the 1, 2, 3, 4, 5. I follow this route like this, right? So I can take any route along the different links of the network, and this route is referred to as a walk, okay? And in an undirected network, you can go either way. You can go from here to here, then you can go backwards as well. And you can see, in fact, that's exactly what I've done over here. I went from this is here to here, and then back again, right? But in a directed network, you can only go along the edge of the arrow. So that's what's referred to as a walk, and the length of the walk is the total number of hops taken along the route. So suppose I've taken this particular route over here, I've taken 5 hops. So I could have done it in just 2 hops, but I chose to do 1, 2, 3, 4, 5 hops like that, right? And a path is a self-avoiding walk. So which means that you one in which you don't go along any given edge twice, right? So for example, here is a path because I'm going from here to here. I go 1, 2, 3, 4, right? So I don't cross any particular edge twice. And paths become very important in a second. When talking about things as the shortest path length, okay? So you can have many paths between nodes, right? So suppose I am looking from 1 to 3, for example, okay? So I can go from 1, 2, 4, 5, 3. That's a path, right? I go 1, 2, 4, 3. That's another path. But 1, 2, 4, 3 is a shorter path, right? So because here I'm taking only 3 steps, whereas here I took 1, 2, 3, 4 steps. Even though the starting and ending nodes are the same, but I can do it in less time. I can do it in just 3 hops. So the shortest path then is the least number of hops that you need to take along a path between a pair of nodes, right? So for this particular network shown over here, I've shown for all the possible sources and targets, so 1 to 2 and so on, what will be the shortest path? So you see from 1 to 2, I mean, it's clearly 1 because there's only one hop you can take. Whereas 1 to 3, as I just showed you now, there's the shortest part is 3. Even though I can take 4 as well, I can do it in 3, and so on. So this is what it represents. 1 to 4, I can do 1 4. I can also 1 to 5 4, but that's longer. Right? So one can do this for the for every sort of pair of nodes in the network. Find the shortest path line. Okay? So what about here? Okay, just in the interest of time, tell me what is the shortest path between 1 and 3? Oh, yeah, 1 and 3. 3? Yeah, fine. So basically, you have to make sure that you don't go along the opposite direction of the arrow. But as long as you do that, you can work out what is the shortest path length of every pair of nodes in this network. And this actually becomes very important in a second because like here we have computed the shortest path length for all the pairs of nodes in this undirected network. And similarly, you can work out what is the shortest path length for every pair of nodes in the directed network. And once you have this information, you can then talk about what's called the diameter, right? And the diameter is basically the longest shortest path between all pairs of nodes. Okay, so we have worked out what are all the individual shortest paths. We can also work out what is so now that we have the information, so what is the longest shortest path. So for the case of this network over here, we already remember this table over here. We worked out that 1 to 3 is 3 and everything else is like 2 and 1 and so on. So this is the longest shortest path. So the diameter of this network is 3. And the same thing you can work out for this network. So I won't give you the answer. Maybe you can just write this down, draw this network down and try and work it out for yourself. See what would be the diameter of this particular network. This is useful in terms of talking about like the what is like the total breadth of the network when it comes to things like any process that's spreading over the network. Because suppose you want some to look at, let's say, how quickly some process is sort of traveling along a network and so on. If it has a very large diameter, it may take longer for it to spread and so on. But a small diameter, even though it may be very have a very large number of nodes, it means that it can go from one part of the network to another part in much less time. So it gives you some sense of basically the span, of the network. Okay, I think maybe
here I can go from 4 to 1, for example.
you cannot go from 4 to 1 exactly.
So those
We can skip. No, those we'll just set to 0. Yeah.
then it's 4, right?
The diameter will be
1, 2, 4, 3, 5.
Yeah, 4. 1 to 5.
yeah 4. Right. Yeah. Right.
From 1
Sorry?
to 5 does it
So far you have shorter path length.
You have to look from 1 to 5. Yeah, 1 5 is 3. Then 1 to 1 2. So 2. 1 5 is 2. 1 5 is 2. It will be 3. It will be 3. Because again 1 to 3 is there. So. No, you can't go along the same path twice.
Like a 4 to 5 not really coming.
Well, you can do that, but the thing is, can there be a shorter path than that?
4 to 5 is the K3.
Right. Yeah. So okay. So maybe because there's a lot more to cover, and maybe I'll cover that in the subsequent lectures. So maybe we'll stop here. I was hoping to get to some questions. So I have some exercises for you as well. So we'll do that next time. Anyway, now I think you have like some very basic introduction to the stuff. We'll get to the more advanced things over time. So maybe we'll stop for now.